Thanks everyone for the time today. My name is Ranjan. I'm a sales engineer at Julia Hub. And today I just want to talk to you guys about surrogate modeling and really how might you build surrogate models of Acausal systems in general, and how might you do that with Julia Sim. Um, so just to set the brief agenda here. So I thought I could, after giving you a little bit of background on what Julia Sim is and where we are and who are we, and maybe a bit of background on myself. I thought I'd structure the talk this way, just give you an idea of what are the different stages in surrogate modeling, and the key really is automating through these stages, right? And in terms of a user experience, and for most people, I'd say most people, especially in the academic world, we're used to sort of specifying these three stages ourselves, but how exactly might a product sort of automate all of this for you? And then, of course, like talk to you about the different types of surrogate modeling problems, and really, and then after that, what exactly would you do with a surrogate? So first, maybe a little bit of background on what Julia Sim is. Julia Sim is a sort of modeling and simulation product. We call it scientific machine learning for the for our enterprise customers. And scientific machine learning is in our view this sort of confluence of these two different worlds, right? So you have sort of the very traditional scientific computing world, where people build component-based models, check for robustness, check for correctness of their systems, and they rely on robust solvers and so on. And of course, once you build your component-based model, you can then design control. So the machine learning world, I mean, is sort of blown up in let's say the past decade, when talking about non-scientific problems, and of course recently with LLMs and so on. But really, the question is, I think, with regard to the engineering world, how machine learning is supposed to be applied or supposed to be used, and it's supposed in heavy asterisks. So so our sort of view on this, and I'd say a large community's view on this, is this world of scientific machine learning. So can you have simulators that are differentiable? Can you build surrogate models, and use these differential simulators and surrogate models, and apply them to inverse problems? And additionally, we're sort of seeing these nice data-driven autocomplete features like automatic equation discovery, coming up as well. Today's talk is mostly just going to be about surrogate models. And the way Julia Sim is set up to support all of this is it starts off with a base of modeling tools, which are based on Julia, from the SciML ecosystem in Julia, and in particular the modeling toolkit.jl package. But where Julia Sim provides the value is giving you standard libraries that sit on top of this, some of which are open source, and I know our audience uses, but some proprietary libraries as well, right? So how do you build sort of detailed vapor compression systems, battery systems? I know there was a talk earlier on batteries as well, and I'll briefly talk about our take on it, and then multi-body systems, right? And to be able to build, and you could, for example, think about building out a full electrical car system in Julia Sim with these types of components. And we also, in addition to providing model building tools, we also provide these methods as well. So, and the one that we're going to think about today is the surrogate modeling part. But by the way, if folks on the call, just feel free to interrupt me with questions anytime. I really don't mind. So just and this sort of goes into a bit more detail on what the methods are. But really today, we're thinking about surrogates. So Julia Sim itself, the way you sort of use Julia Sim is through a graphical application called Julia Sim Studio, which is a drag and drop component based model builder. And here this is a semblance of what that might look like. And in addition to sort of the drag and drop builder, we have an an interface, a domain, several domain-specific interfaces, and this one's the Julius and batteries one, and this particular simulation is showing you is trying to model the variation you might see in a battery pack. So really, say you have this distribution of state of health and lifetime amongst all the cells in the pack, and this is something that as a pack designer you might be concerned with. Okay. And of course, since we provide these standard libraries, you can sort of connect them with in sort of a multi-physics simulation as well. And of course, I'm happy to elaborate on these capabilities. If folks have questions. And sort of similar story with the HVAC library, and we're happy to elaborate a bit later. But these are the two big ones that we sort of work on in-house and provide to our customers. So surrogate modeling, how exactly does that have, Julius Sim is built upon Modeling Toolkit, and Modeling Toolkit is an Acausal modeling framework. So and hopefully in this talk we'll get a sense of how we think about surrogate models in the context of Julius Sim and Modeling Toolkit. So I want to present two different axes of surrogate modeling to you, and the first sort of axis is sort of the stages that you go through while building these surrogate models, and we sort of see it in these three different stages here, broadly speaking, right? Like, so the first stage is data generation. So how surrogate modeling needs training data. And so where does this training data come from, right? You could, for example, get it from the field, or you could simulate a physics-based model several times throughout some sort of chosen input space, right? And this is the design of experiments piece that I'm referring to here. And of course, from a system standpoint, how do you ingest all these different input types? And a system needs to be versatile enough to be able to take all of these things. And so if it's a dynamic model in various formats, or let's say if it's field data. Now, of course, the data generation part is all about the design of experiments, like really how well you pick those points. But you also need a little bit of this is sort of where this is one of the places where you might inject some physical intuition into how exactly you get those physical you do your data generation, which are the parts of the space you care most about, and in some ways how do you bound the input space, and that's a big part of like applying things about your model, because given that you built the model to generate an accurate surrogate model. A second bit's on training, and I sort of include how do you choose the architecture or to build a surrogate model. In Julius Sim we provide this proprietary architecture called the Digital Echo, which is sort of reservoir computing based. But really there's a bit more to training in terms of how do you pre-process the data and set it up, and how do you post-process what is coming out of your neural network architecture, right? And a lot of little things in between. So this is sort of the next big sort of item in the surrogate modeling training process. And the final and perhaps the one that the model designer cares most about is what do you do with the surrogate model, right? I mean, do you embed it in a design optimization loop? Do you perform sensitivity analysis? Sometimes when you're doing global sensitivity analysis, you need thousands and thousands of simulations to do that sort of statistical analysis. And that's exactly where a surrogate model comes in to make all of those function evaluations faster. And then finally, on a systems level, how do you want to export the surrogate model in, either within your own simulator, or within your own team, or beyond that, right? And to be able to support other simulators. And we'll look at this idea of functional markup units, which we'll briefly introduce later. And of course, like the other really nice thing that people like to do with surrogate models is to explore the parameter space. and gain intuition for how the model behaves through the parameter space. And a web app is a nice sort of way to do this as well. Now, of course, all of those surrogate models that we're speaking of today, are causal systems, or and in some and by extension dynamical systems. And one of the key things is that usually you'll find that accuracy will scale with more data, as long as the data is well chosen. And so to generate more data on the fly and demand, or for example, even in some kinds of surrogate modeling paradigms, you can perform your design of experiments and your simulations all in parallel. And to be able to do that with mass, to be able to request compute on demand as part of the entire workflow and the offering that we provide with Julius Sim. But the second axis that I want to mention are the different problem types of surrogate modeling. So there are two types. There are two paradigms here that I want to refer to. One's what I'd call a system level paradigm, and this is this is sort of very well defined in scope, right? So you have a system, and you'd like that to study how that system varies, across its parameter space, right? And the way you do this is take your chosen parameter space, simulate the system against many chosen parameters, you using your design of experiments. And then hopefully your surrogate model interpolates quite well between those parameters, right, in terms of its dynamic behavior. And this is something that this is exactly the type of surrogate model that you might want to use for design optimization and sensitivity analysis. So this is sort of this one paradigm, but then the second paradigm, which is far more interesting and a far harder surrogate modeling problem, is called the component level surrogate model. So if you have an elaborate component-based system, can you then take a small piece of it, right? And that small piece of it could, let's say in a vapor compression system, could be, let's say, the heat exchanger component, or any of, or any component you could conceive of in a system that is performing that runs quite slowly. So let's say if when we talk about FMI, we'll talk a little bit about co-simulation. But if you had this elaborate co-simulation co-simulation setup, what if one of the models that is quite slow? So this is the type of type of surrogate model that you might want to employ there. And really, it's the reason why it's a lot harder is because you really need to think about causality and acausality in this context. So if you have a system that for example, with a certain direction of flow, can, and let's say the direction of flow switches in the middle of the simulation, right? And how do you account for both of these behaviors in the surrogate modeling paradigm? And really, like the surrogate model would have to be exposed in some ways to all of the different system configurations or different types of causalizations of the system in some ways. And that to some extent is feedback from the modeling system itself, which is why we like to work with such a transparent and powerful system such as Modeling Toolkit. And really the other question is, even if you're validating this type of component in open loop, how exactly do you choose the input signals to perturb the system, given, of course, the system is non-linear. If the system were linear, you could consider a certain set of frequencies and so on. But since it's non-linear, how exactly do you do that? These are all sort of open questions, but these are things that we're working on in-house. But these are the two axes that I want you to think about, the different stages of surrogate modeling and the problem types, to give you a sense of the richness of the problem. So what I want to do in the rest of this presentation is to give you an idea of how we do how we tackle both of these types of problems today, and tell you and sort of tell you how and and what is coming next, right? Like in terms of putting all of this together. And yeah, and again, we'll open the floor for questions immediately after. So let's perhaps talk about the system level surrogate model. And so one of the first system level models that we targeted, and we've targeted a number of different models in collaboration with our and with Mitsubishi Electric Research Lab is can you accelerate a vapor compression system across by interpolating across its parameter space, and it turns out you can, and you get 2 orders of magnitude speed up, and but the key thing is you also get a really accurate surrogate model, and even with about 100 to 1,000 points, it is quite possible, depending on the system, to get good accuracy, or within the typical accuracy that we check for is within 5%, and you can typically get within 5% at 100x speed up, which is quite nice. To maybe give you a sense of how that works, I will show you. Let me show you one of the demos that I've prepared here. Let's maybe make that bigger. So this is another sort of system level surrogate modeling problem that we've set up, and this is this is one of the examples from our documentation, and of course this notebook is running on Julia Hub, by the way, as you can see the URL here, but I mean, like, let's consider this sort of this really stiff system, this nonlinear chemical reaction system, which is given by a couple of PDEs. It's called the Brusselator, which is a fairly popular autocatalytic reaction system that's used as a model in other fields. But we, it's described by a set of 2 PDEs with some forcing and initial conditions. But let's consider the problem of trying to build a system level surrogate model of this, and to show you how, with every sort of surrogate modeling problem, you need to define some sort of input-output paradigm, right? And for example, and let's maybe consider some of these parameters as inputs, and let's take some slice of the solution as the output that we care about, and of course, we can go through and import some of our packages here. And one nice thing to sort of notice is that JuliaSim and modeling toolkit and our entire sort of and this entire ecosystem blends together quite perfectly, and you would just generally interact with these things just like you would interact with other JuliaSim packages, Julia packages. And I've defined this PD system in this piece of code here, which I've saved to disk, so as to not clutter the space. But the way you set up a system level surrogate is to think about this parameter space object, and and the parameters, this parameter space object is just a simple sort of Cartesian box specification, right? So what are the lower bounds of your parameters? What are the upper bounds of your parameters? And how many samples do you want from the space here? And of course, the upper and lower bound, while informed by physical intuition, the number of samples is something that you don't really know a priori, right? And this is part of the automation piece that I'll talk about later on. But this is how you construct a parameter space object. And once you have that, you can then, and this is not code I'm running right now, but you can then you can then set up a batch, a data generation job. And what this piece of code is going to do is spawn an instance on Julia Hub and run run 500 simulations in parallel, and then once it's done, it'll save the results as a Julia Hub data set. Excuse me. So this is sort of, just within 4 or 5 lines of code, you can like spawn a massive number of simulations. But and then of course the data is auto saved into Julia Hub data set, which is quite nice. And we can download this data set and into what we call an experiment data object. And this is this is sort of our design for any sort of simulation. You can simulate a model multiple times, and all of the data gets saved into an experiment data set within Julia Sim. And of course, now that you have this ED object, which is essentially a dictionary, you can then plot a few samples and see how the system looks like, with a simple command. Now, to train the surrogate model, it's really what you're trying to do is we've sort of automated some of this for the end user. The way you build train a surrogate model is just by calling this function digital echo, and this macro at train here is just wrapping all of this up so that this is a piece of code you can then sort of spawn in a training job for, right? So just like how we did data generation, we spawn another training job on Julia Hub, and this will again be spawned off as a job on Julia Hub, and once it's done, it'll save the surrogate model as a Julia Hub data set as well. And this is also something we can download as a data set and then examine. So you can see that this is you can see that this is there are 2 things to notice here. We call it a digital echo problem with a certain number of parameters, and it also has a solver in it. So this sort of tells you that this is a dynamical system itself, which makes sense because we're creating a surrogate model of a dynamical system. Now we can start quickly. We can inspect the results here by running a bit of validation code, and you'll see that you don't really see this ground truth line here in orange because it's literally line over line. So and you can inspect that the surrogate model has actually trained properly. But now the key thing that I was referring to earlier in terms of using system level surrogate models is how to use it in a downstream sense. And let's say in this particular example, I want to do some type of parameter estimation. And so to do a little comparison, let's set up the same problem running the full auto model as well as the surrogate model, and let's to keep things fair, let's run both for just for 10 seconds and see how far they get, right? And when we run the surrogate model, when we run the calibration using the surrogate model, you see that the surrogate model, while incomplete, of course, in 10 seconds, is getting quite close. And so you can see that the surrogate model has made a bit of progress. However, a calibration using the full model within 10 seconds has barely even started. So you can you can see that over here, and you'll see that with the surrogate model, you can see that with with a little GIF here that the surrogate model is takes a second to think, and of course, depending on how accurate you train the surrogate model, it might even take a few wrong steps, but it'll eventually either converge or give you something close enough to the original answer that you can then use the result of the surrogate model to initialize the simulation on the parameter estimation using the full auto model. And if it's reasonably close and you're using a nice method, you could converge very quickly. And this is sort of a fairly natural, intuitive design workflow that we recommend to a lot of people and a lot of our customers. So that's Yeah, so that's how you would take a full auto model and perform sort of a system level surrogate model within Julius Sim. Let's see. So as I mentioned earlier, part of the reason part of the reason you want to use Julia Hub for all of this is, can you get this on demand compute and simulate the surrogate model, and you could do with this in the system level surrogate modeling paradigm. You can simulate all of these things in parallel, and in also the component the component level surrogate model. You can also do a number of things in parallel, but this is, it's sort of straightforward to see how you could do it on the system level as well. There are a couple of details in the component level that I'll get to, but broadly speaking, you can do you can sort of do this and get, and in some ways you can think about amortizing 100 simulations at the cost of one, or 1,000 simulations at the cost of one, conceptually, so that you can just train the surrogate model. And the other sort of aspect we want to show here is this experiment tracking, which is this nice way of thinking about excuse me, thinking about the neural network training, and you might see that if you're trying to search or do a full hyperparameter search space, you can then you can sort of then get the you can then keep track of all of your experiments and then see which one gives you the best results and so on. And finally, you can see that we can input a number of different dynamic model types, but really you can see that this nice little animation here is shows us how you get some sort of validation, and even if you plot a bunch of outputs against each other, in this sort of state space plot here, you can look at the trajectory of the model in state space, and then see the surrogate nicely validates against that. And we provide some of these nice visualization tools as well, so that you can get an intuition for how this works. Okay. Maybe I'll pause for a second to see if there are any questions on the system level model, and before I move on to the component level. Any questions so far?
I haven't seen. I have a lot of, but I can wait until the end.
Okay,
It makes it easier for me to edit the video.
Yeah, absolutely. Yeah. Perfect. Okay, so the component level. So the second part is the component level surrogate model. So, so as I mentioned a little while earlier, excuse me, the component level surrogate model is a way of taking a component within a large system simulation and then building a surrogate model of that. And you can see that component. You can sort of if you look at this plot here, we have sort of a very simple 2-input system, and what we want to do is try and validate this system, train a surrogate of this model, and then validate the surrogate model within closed loop control. So you can see, if you look at the picture on the left here, just like how I showed you the notion of a parameter space, we have something called a control space, and this control space object needs a few things. So one thing is, the upper and lower bounds for the signals, of course. But the other thing that it needs is some type of algorithm to traverse through all of the control space. So, for example, it can keep generating random, control signals from this upper and lower bound control space. However, that's sort of a brute force approach in some ways. So you can certainly do a lot better, and we'll refer to that a little bit later. But if you have an idea of what your control signals are going to look like, or if or how exactly your original model is validated in open loop before you put it in a controller. These are the types of things you can specify to the surrogate model, and then it'll probe the original system this way and then try and learn from it. And there's a lot of stuff going on, under the hood here. But this is sort of to give you an idea here, and you'll see that if you look at the plot on the bottom right, that the surrogate is, while not perfect, is largely able to be constrained by the controller in a very similar way. Yeah, so this is a work in progress for us, and we have quite a few steps here in order to make this first class. But at this stage, what we can say is that we have all of the pieces in place to be able to do this correctly. And the second sort of example I wanted to show you is an example of a surrogate model of a battery system. So our battery system, a battery system will take in. I believe it takes in just one input, which is a time varying voltage, and then you measure the current and state of charge as the output. And the battery system was trained with exactly the system I showed you in the previous slide, and typically in batteries, you work with things called drive cycles. So the power draw, or which represents sort of the power draw, the usage of the battery through a realistic driving scenario, right? And the driving scenario we're trying to look at is maybe how do you go from the Julia Hub headquarters in one part of Boston to MIT, which is in another part of Boston. I mean, well, they're both in Cambridge, but you know what I mean. And to give you a sense of how exactly you do this, we provide this app that lets you pick a distribution of control signals. And there's a lot of little parameters here that you currently have to manually play around with, which we manually play around with, and we're trying to completely automate this. But really, when you're thinking about something like when you're thinking about a component level surrogate that takes in dynamic inputs, you sort of have to think about the state space of the system, because depending on where you are in the state space, the control signals are going to affect the system differently. And so you have this nice little state space plot here, and this line here represents our test signal in some ways, or our test trajectory, and you see that it falls within the state space that the surrogate model has seen. So this this yellow portion is what the surrogate model has roughly seen in training, with a lot of little gaps here and there. As you can see, there's a lot of gaps here, but since it's within what the surrogate model has seen, the surrogate model knows enough to interpolate and get such a really sort of complex system here to look correct. And the bottom here line here is the state of charge, which gradually goes down. But the current draw from the battery is a remarkable signal, and the fact that the surrogate model is able to get that correct has everything to do with the sophisticated machinery that we put into the trading here. Okay, and to show you a little bit, to visualize this in a different way, you can look at, we sort of performed a little 3D simulation here of the battery zipping along with the surrogate model with accurate predictions. And you can see, this car is moving uncharacteristically quickly, and the car on the right hasn't left the parking lot, and this is just really to show you what the, if you use if you used a full order model to do this type of simulation, that you're much slower than using a surrogate, which but this fast car gets a few laughs, so I thought I'd show you guys. Yeah, you can see the surrogate model prediction is a lot faster as well, as you can see the trace here. So okay, the final piece that I wanted to touch on is surrogate models and FMI, which is the functional mockup unit. Julius Sim supports the FMI standard. A lot of folks, a lot of we're not unique in this. It's supported by 180 different tools, but the FMI is a sort of as a standard to exchange dynamic simulation models. Can you build can you build can you export your systems as binaries that can be important to other simulators, and this is something we support. And so this enables a couple of workflows that we think are really useful. So you can build your model in Julius Sim using our standard library components. Build a surrogate model of it, and you can export that as an FMU that you can be exported as a fast block in an external simulator. And sort of the corollary or the related workflow here is if you have a large component-based model with a slow system, you can then export. You can then you export that system as a functional mockup unit, which we can then import into Julius Sim, generate a surrogate model of that component, and export that surrogate model as an FMU as well, and import that FMU into your external simulator. And so yeah, you just have a faster version of the same FMU in theory, right? And yeah, so these are sort of the two workflows that this type of thing enables. So to demonstrate that a bit, I'd like to show you this demo here, which sets up a simple vapor compression system, which actually my colleague Avinash, who's also on the call, built. So props to him. And what you can do now is you can, once you specify the system here, and you can do this. Avinash provided us a very simple single level vapor compression cycle command to set up the system. You can then grab the ODE problem from that modeling toolkit system, and specify the input parameters over which you want to train a surrogate, specify the number of training points, just like you had seen before in the system level surrogate example, and then define the parameter space object, the sim configuration object, and then you run the simulation. But I've commented this out because it's for the purposes of this demo, and then you can run digital echo on it. And in this case, I've run it only for a few epochs, but really you would need thousands of epochs to run this. But why I wanted to show this to you, and after showing you a little bit of validation, is this final bit here. So you get you can see the validation is nearly perfect here, but even with 100 epochs, but we provide this one-click validation of the surrogate model, and that surrogate model is exported here, called digitalecho.fmu, and it's compiling everything down into an FMU as well. And what I wanted to show here is the ability to then import this FMU into an external simulator here. So this I'll exit this and show you. So I'm sort of running. I'm importing this from from Python, and running the FMU with a with a sort of well-known FMU simulation tool called FMPy, and you can just hit simulate FMU, and then this will just load up. You can see there's a warning here that we need to clean up, but like you can import this FMU here, and after some logging information, it'll run fairly quickly and give you the results. So yeah, so this is just sort of a demonstration of how this is meant to work as a full system. And of course, like if you like the model you've built in JuliaSim, either be a surrogate model or a regular component-based model, you can export it as an FMU with this one-click functionality. Yeah. The final piece I wanted to mention is, on our next steps. Really, while we have thought about these three different stages of surrogate modeling, what's really, really powerful is to have feedback from each of these stages, into the data generation process, because usually you don't know how many simulations you need to get an accurate surrogate model, right? So, but the way you can try and automate that is getting some, let's say, validation loss from the training, or some sort of proxy for global error from the training into, and you can then use into the data generation loop, and this is sort of commonly called active learning, and what's even more powerful is to take information from how you would use the surrogate model. So for example, let's say you want to do it for design optimization, you find that it's not quite converging or not quite accurate enough to be useful for design optimization. You can then penalize the surrogate training by this metric. And usually the way we like to think about this is, if you're usually when you build a physics-based model, you're running a bunch of different tests to make sure the model is correct. And you can use these same tests on the surrogate model and embed that as intuition or feedback into the surrogate modeling process, so that the surrogate training can then be penalized with the results of these tests, and you can sort of set up this active learning loop where you sample more data points from the regions where the surrogate model is not as accurate and not as nice. Yeah, so that's sort of how that's sort of how I would think about our next steps, and yeah, there's a lot of exciting things to come ahead, and we're looking forward to sharing with you and the world how we accomplish this and make surrogate modeling easy for engineers, for design, and sort of even operations, or if you want to embed your model within embedded hardware and so on. But yeah, that's all I have for today, and